Hi, it's Mr. Anderson. Today I'm going to be talking about plate tectonics. What's always interested me about plate tectonics is it's a fairly recent science. In other words, not until the 1950s were we sure that the plates were actually moving. One of the first people to suggest that was Alfred Wegener, and he actually worked right around 1920. And what he said is that if you look at the different continents, here's North, South America, Africa, Eurasia, they tend to fit together on almost like a puzzle. And so he was the first person to say maybe all of the plates were connected at one point. We now know that that's true and that was called Pangea. The problem is that Wegener thought that the continental plates, which are actually really large, and the oceanic plates, that the continental plates were somehow pushing their way through the oceanic plates. Oceanic plates are really dense, and so other scientists at that time said that they wouldn't have the momentum to be able to push through the rocks, and so the theory kind of fell apart. And so Alfred Wegener actually didn't spend most of his career studying plate tectonics. He ended up being a meteorologist for most of his career and ended up dying in Greenland. It's a crazy story of how he met his end. But that's not what I'm going to talk about. I'm going to talk about plate tectonics. So when did the science really take off? Well, there were two things that took place. First of all, we started looking at fossils on one side of the Atlantic and on the other, and we find that they actually matched up. So that's a good piece of evidence. But the best evidence came by looking at the rock in the oceanic crust, so in the floor of the ocean. There's rock underneath the water. And we started looking at the magnetic fields that are stored in the rock. So as the rock is actually being formed, we can look at the magnetic pole or the polarity in the rock itself, and our poles will actually switch back and forth. So that occasionally north will become south and south will become north, and that's actually recorded in the rock. And so we could look at how old the rock was, and we could see how fast it's actually moving. And so this is a cool study because this right here, to kind of wrap your head around this is right down the middle of the Atlantic Ocean. These are going to be the youngest rocks. So in this diagram, the youngest rocks are going to be in red, and then the yellow is going to be older, and then the green is going to be older yet, and the blue is going to be older yet. So what does that mean? Well, it means that the youngest rock are actually right at the center of the ocean, and then it's older the farther we go to the edges of the Atlantic. What does that mean? Well, it means that North America and Eurasia were connected, and they've been pulled apart, but they're not plowing through the oceanic crust. New oceanic crust is being made in the middle, and so it's actually pushing them apart. Now, how fast does this happen? I remember reading once that the plates move about as fast as your fingernails grow. And so you're not going to see the plates moving, but over millions and millions of years, it actually ends up being quite a bit. Now, another way to look at where those plates actually exist is to look at where earthquakes occur. And so earthquakes occur where you have rock either being pulled against itself, pushed against itself, or sliding past itself. And so when that rock gives a little bit, that's an earthquake. And so if you look at where the earthquakes are centered on our planet, they're actually centered, well, here'd be the Atlantic, so right along that mid-oceanic ridge. We also see them around what's called the Ring of Fire. So if this is the Pacific Ocean over here, so this would be Alaska, down the western seaboard, this would be the San Andreas Fault, all the way down to South America, and then all the way back to Japan again. So we have what's called this Ring of Fire. Now, why do we find earthquakes in some areas, but in some areas we don't? Well, that's where the plates actually match up. And so if we look in the U.S., which we're pretty familiar with, where would we find a lot of earthquakes? Well, in California. So why do we have so many earthquakes in California? Well, here's the San Andreas Fault. It actually cuts California right in half. And so on one side of that, we have a plate moving in one direction. On the other, it's moving in the other direction. And so when they slip past one another, then we actually have an earthquake. And so these are the major plates on our planet. We have like a North American plate, a Pacific plate. This is the Juan de Fuca plate right up here. But all of these plates, as they move, shape our planet. And they also give us earthquakes and show us where there are places where it may be not safe to live. So for example, we just had a huge earthquake in Japan, which causes a great tsunami. Why is that? Well, it's right here located on the junction of almost 4 plates that are all moving past one another. And so plate tectonics tells us that plates are moving on our planet, but there are 2 types of plates that you should be familiar with. The first one are called continental crust or continental plates. Continental plates in general are made of granite. Now granite, the best way to think of granite, if you've ever been to Yosemite, this is a giant piece of granite. Granite is going to be a lighter rock Continents are very big, so my fist is going to represent a continental plate. And they're also a little less dense than the oceanic plates. So this is oceanic plate. This is from lava forming in Hawaii. Oceanic plates are made of basalt. And so basalt is going to be a darker rock, and it's going to be a more dense rock. And so what does that mean? Well, if you have a continental plate hitting an oceanic plate, the one that's more dense is going to be the oceanic plate. And so the oceanic plate is going to be forced underneath the continental plate. And so a great example of this would be on the west coast of the United States. We have this, which is the Pacific plate, going underneath the North American plate. And so this would be that dense oceanic crust being pushed underneath the continental crust. And as it does that, it starts to melt as it moves farther and farther down, and eventually causes volcanoes. So Mount Rainier is an active volcano. Mount St. Helens is an active volcano. And why is it active? It's because the oceanic crust is being forced underneath the continental crust. It's melting, and then it's causing that volcanism on the surface. And so almost all of the geology, large geology on our planet, can be explained by looking at what kind of a boundary it is between the two continental plates. So first of all, or oceanic plates. First of all, let's think about what could happen. So let's say we have two continental plates that are coming together. Well, they're both massive, and they both have roughly the same density. And so when they run into each other, it's almost like two cars running into each other. They'll just crumple up and get larger. So where's an example of that on our planet? The Himalayan mountains, which is formed where India is slamming into Asia. And so that's two continental crusts. What else could happen? Well, we could have two continental plates that are actually pulling apart. We call that a divergent boundary. What does that create? That creates a rift. In other words, when two continental plates pull across from each other, that causes a rift. And so the Rift Valley of Africa is an example of two divergent continental crusts. What else could happen? Well, we could have two oceanic plates converging. So what happens when we have two oceanic plates converging? Well, one of them will tend to buckle under the other, and then we get volcanism as well, and we're going to have islands forming. And so if you look at the Aleutian Islands, which caused that arc off of the coast of Alaska, it forms like this. We have two oceanic plates running into each other, one's being forced under the other, and then you get this volcanism. What happens if we have two oceanic plates that are moving away from each other? Well, what's that? That's seafloor spreading. So right here in the center of the Atlantic, remember, we have two oceanic plates that are moving past one another. And remember, the Atlantic will get bigger and bigger and bigger just as a cause of that. And then we could also have a transform boundary. That's when one is sliding past it. An example of that would be the San Andreas Fault in California. So the one thing I have told you is that that's how we get all the geology on our planet, or the rock formations on our planet. But what I haven't told you is what causes that. So what causes that is convection currents. In other words, this is magma down here, so this is molten rock, and so we have convection currents, and a best way to think of that would be like in a lava lamp where you have the oil moving up and down. So you get convection currents where we have hot areas moving up, cool areas moving down, and that's actually driving the movement of these plates. One other thing that I haven't talked about is what's called a hot spot, and those are kind of pretty cool. This would be a hot spot right here. So Hawaii is actually formed by a hot spot. That's just an area where the magma happens to come a little bit closer to the crust. And so Hawaii is formed by a hot spot, but really close to home, Yellowstone Park is actually situated over a hot spot. And so as the crust moves over it, that hot spot stays in the same location. And so Yellowstone Park will actually move its location over time. We can track where it was in the past, just like Hawaii will move. The big island of Hawaii is where that volcanism is actually taking place. And the reason it trails off to the edge of Hawaii is that there's been more erosion. And so that's a brief introduction to plate tectonics, but I hope that's helpful.